Good morning. I used to sincerely enjoy grading. I don't enjoy grading anymore. Assuming that I can give everyone's, not because you did poorly or anything, it's because you didn't. But there's 300 plus students, and if I give 5 minutes to every student, it's a lot of minutes. Oh man, so that's not done yet. I've still got the last page to grade. I'm gonna go home right after class, put on some movies, grade the exam. I'd go crazy if I didn't have something on in the background. So hopefully the idea is that I get those graded by sometime midday tomorrow, and then I get grades recorded and back to you on Wednesday. So those are coming. I told you about my wife saying that it looked like a bush was growing in our front yard. And so of course this is actually my Christmas tree. That just, we really are just trashy people. Someone in 10 o'clock was like, you don't rake your leaves either. Best part about this picture though is look right here. There she is, just checking out what I'm doing. That was this morning. She's just, she wishes she could have come out with me.
How about those Oscars, huh?
What's that?
The Oscars.
How about those Oscars, right? Wow. DiCaprio, finally, right? Okay. My wife was also like, why are you telling them how trash he was? She was actually a little mad about it. So anyway, let's see what else. Oh, so interesting thing. This is as it pertains to something we've talked about in here. So I was reading The Economist this weekend. I was reading about tariffs in India, which is something I guess that you just do once you get older. You read articles about Indian tariffs, and so I didn't read it word for word. I was skimming it, but one thing I noticed was that, all right, so tariffs are really high on alcohol imported into India. And so what happens is, of course, taxes have other consequences. And so what people do is they make their own homebrew booze line, apparently. And so last year, so when you make your own homebrew booze, that can be a little bit dangerous because you don't have the quality control that is often associated with bigger breweries and such, or distilleries. And so last year, and this isn't, I mean, it's not funny at all. Last year, 1,700 Indians died from drinking methanol-laced homebrew alcohol. And so we had talked about how this is an issue. Methanol being in booze, basically, it can make you go blind, but it can also kill you. And so it's still a significant issue in other parts of the world. So I thought that was at least interesting as it pertains to what we've talked about in class. Okay, so let's see. All right, so one more, all right, so I guess 2 more things. So on an exam in the future, if I say in 10 words or less, describe something. No joke, some people wrote in like 6-point font over 100 words. Not necessary. This time I didn't take anything off, but after like 15 or 20 words, I'm gonna stop reading it because, I mean, you got full credit for a 1-word answer in this case. So just keep it simple. I'm not asking you to write anything long as I go. And then finally, I don't know if I've mentioned this in here, but I haven't been very satisfied with the textbook thus far. It's my first time using this textbook. I thought that the questions would be better. The end of chapter problems, I don't think they're actually that good. I haven't told you this, but I want a grant to start developing an open source organic chemistry workbook, basically a huge workbook full of good problems that will be made available nationally to all schools everywhere. And so I figure I can kill 2 birds with 1 stone if I start making those problems as we go, right? And so the reason I haven't posted any extra homework thus far is because I want to actually make my own homework problems for you. And so it's taken me a little, with the grading, it's taken me a little while, obviously, but with spring break coming up, I'll start shooting those out as soon as possible. So hopefully, and plus those will probably be perfectly in line with how I write exam questions, right? So that should be really good. Okay, so let's see, we left off last time we had just learned how to use our hands, to use the thumb rule, basically, in assigning either R or S to a given molecule. And so I wanted to go over maybe a few practice examples of this. So, for example, if we had a molecule that looked like this. Well, the first thing we ever want to do, if we got to figure out if there's, if it has R or S stereochemistry, we got to figure out, is there a carbon that's bound to 4 different groups? In this case, is there? There is, right? So that central carbon that I've shown with geometry is definitely bonded to 4 different groups, and so we do have stereochemistry. I'm also going to start throwing in some naming as we go. I said at the beginning that I wasn't going to focus in on naming too much on exam 1, and so we're just going to kind of learn it organically as we go, right? So we'll use it in class, and hopefully we'll just kind of pick up on it. So one thing, I guess the one thing we'll introduce today is we've got a bromine substituent. Now, if we have had a methyl substituent, or at least a CH3, we call it methyl, and then we have ethyl and other substituents that we have names for. For a bromine, if it's a substituent, what are we going to call it? It's bromo, right? What about if it's a chlorine? Chloro, fluoro, iodo. It's just basically the first part of the halogen and then an O. And so in naming this, we name it like anything else. We would say that it is, what's our longest carbon chain in this molecule? Yep, and so again, since there's one substituent that's not a carbon or a hydrogen, we'll number to give that bromine the lowest number. So we have 4. So our name will be butane. And then what we'd say is that this is 2-bromobutane, right? And so basically we're just signifying there's a bromine at the 2 position. But we also have possible stereochemistry. And so if we're going to name that, well, first off, we have a hydrogen. If we have a hydrogen substituent, we know automatically what priority is that. Yeah, that's automatically the lowest priority. Nothing comes lower than hydrogen. So that's going to be number 4. And then also, we've got a bromine. And so what is that definitely going to be? It should definitely be number 1 because it's heavier than carbon. And so there's nothing there that could be heavier. And then between an ethyl and a methyl, what's going to be higher priority? It should be the ethyl, right? Because in the first case, or in the case of the ethyl, we have a carbon connected to another carbon, but then the methyl is just a carbon connected to hydrogens, and so the ethyl wins out. So we'd say we've got 2, and then we've got 3. Okay, so using our thumb rule, what we can do is we can say, well, let's see, our hydrogen's kind of coming out towards us, and so if we align our thumb this way, and then we curl our fingers, can we count 1, 2, 3 with our left hand? So I see here I am kind of starting at 1, and then the next number I get to is 3, so that doesn't work, so I can go with my right hand, and so now we start at 2, 3, 1, and so it's our right hand that's going to allow us to count 1, 2, 3, and if that's the case, what's the stereo center? It's an R. All right, so we know that this is an R stereo center. In our naming, we've said that every individual molecule gets its own name, and so the way we indicate that in the name is we say that this is R2-bromobutane. So basically, we have to give a stereo designation to indicate that this isn't the opposite form, which would be S2-bromobutane. Okay, so let's see. Another example. Okay, so we've got a double bond here. Looks like that. Yeah?
For the other one, isn't the hydrogen in the front of it?
Yep.
So would you put them in the back to do the...
So you could also do that. I just think it's easier to use the thermal. So what you could say is, all right, so that hydrogen is in the front, and so what I've got to imagine doing is what would my perspective be from the back, right? Because I want to hide the hydrogen from my view. And so in that case, I would count 1, 2, 3, and so from my perspective, that is clockwise, right? And so if it's clockwise, is it R or S? It's R, right? And so it's the same exact. That's why I prefer the thumb rule, because otherwise you've got to start imagining yourself in different places and then counting to see if it's clockwise or counterclockwise. So both methods would get you to R. Yeah. Okay, so our next example. Well, first off, do we have a chiral center? Okay, so I'm guessing you think that this would be a chiral center. Let's see if that's the truth. So if we consider this to be a chiral center, we've got one group here. Well, we'll just mark them. So we've got one group here, one group here. So there's two other groups. Now, as we count around the other groups, we see to the bottom left, we've got 1, 2, 3. To the bottom right, we have 1, 2, 3. And so in reality, is that carbon that we've designated the chiral center, is it bonded to 4 different groups? Now, there's no way to tell the difference between going to this side or going to this side, right? It ultimately is just going to wrap right back around, and nothing's ever going to have a higher priority. And if nothing ever has a higher priority, is it actually a chiral center? It is not a chiral center in this case, and so that has to do with this plane of symmetry, ultimately, that we have running down our ring, and so we say there's no chiral center. So when you're doing this, don't get ahead of yourself. Make sure that you've correctly indicated what chiral centers there are present in the molecule. I can quickly and easily throw in a chiral center, so I could say basically the same thing, except now it'll look like this. So we put an oxygen in the ring. All right, so now as we count down to the bottom left versus the bottom right, are those different? They're definitely different. The second atom here is an oxygen, the second one there is a carbon, and so we can assign them different priorities, and ultimately it is a chiral center. All right, so if we want to name our priorities on this carbon, we've got a hydrogen. What's number 4? Definitely hydrogen. Always hydrogen is going to be our lowest priority. So then we've got 3 groups, all that contain a carbon as their first atom, right? So that doesn't help us. So we have to go to the second next atom that is heaviest. And so if we look here, we see that the second atom is an oxygen. Do we have anything heavier than a carbon off of either this group or this group? We do not. And so we know for sure that the side with the oxygen, since it's the heaviest point of second connection, is going to be our number 1 priority. And so then finally we have this group versus this group. Now this group we consider, this carbon right here, we consider connected to how many carbons? So we consider it connected to 3 in terms of priority. So we say it's connected once here, but then it's connected to this carbon twice. And so we just pretty much say it's connected to 3 carbons. It's the first carbon, and this is 2 times 1. So 3 carbons. This is connected to just 1 carbon. And so what's going to be the higher priority? Should be the top one, right? The one that's bonded to more carbons in this case. So we'd say this is 2, and this is 3. Okay, so we need to assign R or S, and again, we can use our thumbs. So let's see, our hydrogen's coming towards us, and so if I use my right hand, can I wrap 1, 2, 3? I don't think so, but if I use my left hand, my thumb's coming towards us, can I wrap 1, 2, 3? Yeah, if I can start at 1 and go to 2 and then 3. And so if I'm using my left hand, which enantiomer is this, R or S? Most certainly S. Okay, so that's going to be an important skill. Basically find the chiral center and then name is that an R or an S chiral center as we go. All right, so I also want to point out there are 2 ways that you'll commonly see enantiomers drawn, and so I actually want to give a little section to this. I don't know why. Am I drawing too far to the projector's off kilter today. So there are 2 ways to draw enantiomers. And so I've alluded to both thus far, and so what we're basically going to do is we've drawn R2-bromobutane above. What we want to do is show S2-bromobutane in a couple of different ways. And so one way that we've been doing it thus far is I've been drawing a mirror, and then basically we've just been looking at the mirror image. And so that definitely works. So the first way we'll call a mirror plane. And so when we draw the mirror plane, we know that basically everything's going to swap its left and right orientation, but it's going to keep its front-back orientation. So your nose stays on your nose, but your right hand becomes your left hand in the mirror. And so our molecules do the same thing. So from our R2-bromobutane, our ethyl group, will it now be on the left or the right side? Yeah, it should be on the left. It was on the right side. So we've got CH3, CH2. Our bromine that was on a dash is still on a dash. And then our hydrogen that was on a wedge is still on a wedge, just in the opposite direction. And so if we were to go through this process of, we'd have the same ranking, but I guess it wouldn't be R, it would be S. And so if we went through the process, we'd see that this is the S isomer. It's the mirror images. It is not superimposable. They are not identical. All right, so that's fine, but what you're going to run into is molecules are going to become more complicated, and it honestly becomes a real hassle to draw the mirror plane, because you're going to have, when you're drawing these mirror planes, you have to look at every group and then come over and think about, well, what would that be? And if we've got 4 different chiral centers, it's a lot of effort. And so there's one more way that we can do that in my opinion is a lot easier, and you'll see as you go through your careers that involve organic chemistry. So you can swap 2 groups, leave 2 the same. And so ultimately what we do is we could pick, say, the methyl and the ethyl and keep them the same. And so in that case we have CH3, CH2, CH3, and if we keep those the same, to show the other enantiomer, we have to swap the other 2 groups. And so the bromine that was on a dash is now going to be on a wedge. And then the hydrogen that was on a wedge is now going to be on a dash like that. And so again, what we've got is going to be the S form of this. We've kept these 2 the same, but we swapped these 2. And just like I showed you on Friday, that's the problem with enantiomers, right? When we show a model, we only have 2 that are different, whereas the 2 are at the same place, and so that can be tough. It doesn't matter which 2 you swap, so let's say we keep the bromine and the hydrogen in the same place. So in that case, we'd end up with bromine on a dash, hydrogen on a wedge, and if those 2 are the same, we have to swap the methyl and the ethyl, and so now we'll have our ethyl on top, our methyl on the bottom, and again, what we should find is that's going to give us the S enantiomer. So there's 2 different ways to do this. You can either draw the mirror plane, or you can just quickly swap 2 of the groups, and you're going to have the enantiomer. That's really useful in molecules that are, say, really complicated, where you have, let's say we have a molecule like this, and we've got a methyl, a methyl, and a methyl. And so what we would say is, well, just to show the enantiomer, what we can do is just swap out where our methyls are. So it was on a wedge, so now it's on a dash. Was on a dash, so now it's on a wedge. Hold on. Was on a dash, now it's on a wedge. And then finally we have something that was on a wedge, now on a dash. And so what we've done is we've just swapped the methyl group with the hydrogen, right? One, wherever the, I haven't shown the hydrogen, but here we've got a methyl on a wedge and a hydrogen on a dash, and so we've just switched those. Now we've got our methyl on a dash, and our hydrogen is there, just implied on the wedge. Okay, so as we draw more complicated molecules, it can be a lot easier just to switch the groups themselves. Okay, so we're going to move on to section 4 here. And so the title of this is Fisher projections. And now personally, I don't love Fisher projections, and they seem to teach them more than we're going to talk about them in this department. But honestly, I think that they make everything a little more complicated. But I do want you to have seen them. So Fisher projections are named after Emil Fischer, who was a late 19th century organic chemist that did a lot with sugars. And so not surprisingly, Fisher projections were basically developed to be able to show the stereochemistry in sugars. All right, so when we draw a Fisher projection, what we'll do is we will orient our structure so that vertical substituents project away from you, horizontal substituents project towards you. All right, so let's see what that means with an example. And so by the way that this has just typically been done is if you ever have a carbon double bonded with an oxygen, which you do typically in an open form of a carbohydrate or a sugar, that's going to go on top, and so that's why we draw it from top to bottom the way I'm about to. And so we're going to have a carbon. All right, so we have a carbon chain vertically, and then we're going to have substituents off of each of the carbons. And so when we look at the connectivity here, we should be able to point out that, well, some of these carbons have 4 different groups attached to them. And so let's say we would have this one, this one, this one, and this one all have 4 different groups, right? So here we've got an ethyl, hydroxyl, hydrogen, and then all that mess up at the top. So that's 4 different groups. And then if you look at this carbon, we've got hydroxyl, hydrogen, and this stuff, and then that stuff on top. And so we're having a lot of different stereocenters, and so this was developed to show, or at least be a way that we could draw and depict all these different stereocenters. There's a really easy way to remember the orientation. So, honest to God, 10 years ago when I sat in this classroom and I took this class, Professor Elizabeth Harvin taught me this teaching rule that if I remember anything from her class, it has been this. And so, the way you remember your substituents and the direction they go in a Fisher projection is you have to use your imagination. You're in a field and you've been in that field, I don't know, for a while. And what else are you doing? You hang in the field. And so what happens is there's this person you haven't seen in a really long time. And so they appear on the other side of the field, and of course you're excited, right? And so your first inclination is to reach out for them, to hug them. And then as you reach out for them, you start to run a little bit. And of course, as you run a little bit, your head lags behind you along with your feet. So basically, anytime you need to remember what the orientation of this Fisher projection is, just remember there's someone over there that you've missed a lot, and you want to get to them as fast as possible, and so just like that. Wow, right? Okay. That's how you remember that. You should never forget it. I swear to God, that's the one thing I've remembered from a decade ago in this class. All right. I mean, I'm sure I remembered other stuff. I wouldn't, but. Okay, so this is what this molecule is this is D-glucose. And so, actually sugars tend to take a cyclic form, a cyclic form. And so what this ultimately looks like is this right here. And so we've got a picture, so we can number these carbons. We can say that's C1, C2, 3, 4, 5. We're actually going to give 6 to this oxygen, and then we'll give 7 to that carbon. And so the reason we give 6 to that oxygen, it's actually the oxygen on 6 that undergoes a reaction, and we end up with our ring like this. Okay, so glucose actually prefers, and most sugars prefer these cyclic forms, and so in the cyclic form we see it's a 6-membered ring, and so it's a 6-membered ring typically pretty stable. Yeah, it's super stable, right? We've seen that a 6-membered ring doesn't have a lot of the strain associated with smaller rings, and so furthermore, if we keep drawing out glucose, we can draw a 3D picture. And so ultimately that 3D picture looks something like this. And so we end up, when we look at all these substituents, are they equatorial or axial? They're all equatorial, right? And so that's why glucose is so friggin' common. It's because it's able to take this cyclic form. It's very thermodynamically stable because all of its substituents in its chair form are able to take the equatorial position. And the only difference between a lot of different sugars, because there's a ton of sugars that you could end up learning about way down the road, and so there's things like glucose and mannose and lactose, and essentially the only difference is these stereocenters. And so if we change one of the stereocenters, basically if one of these becomes axial, we have a different sugar. And then likewise, if 2 become axial, then that's an even more different sugar. And so there's lots of different possibilities of sugars that we can end up drawing. That's all I want to talk about sugars and Fisher projections. I don't like them very much. Peter? Let's see. It's just error in drawing. This ethyl group is actually a hydroxyl group. That probably makes more sense. Okay, there you go. Good catch. Okay, so that's Fisher projections, and I think there is a lab at some point where you have to look at Fisher projections and determine stereochemistry and whatnot. Okay, so then we get to section 5, and this is, we're basically going to review what the relationships are, and hopefully what we want to be able to do is point at different stereoisomers and determine what their relationships are. And so we'll call this section relationships between stereoisomers. Really raunchy stuff. And so let's just redefine stereoisomers. Those are going to be molecules with their connectivity, same or different? Yeah, so they've got the same connectivity, but they differ in their orientation. And so as we go, what we can say is that, you know, if we have one possible stereo location or stereo center, well, we're going to have a special pair, right? We're going to have two possibilities. But as we go, what we can find is that, well, if we have two stereo centers, the complexity grows exponentially. And so it ends up being basically 2 to the n, where n is how many stereo centers there are. So if you've got 5 stereo centers in a molecule, well, how many possible stereoisomers are there? It should be like 32, right? And so we need to be able to basically classify the relationships between all these stereoisomers that can occur. We're going to boil it down to make it really, really simple. So it has complex names, but we're going to give it the easiest definitions to remember. So first off, let's just say that when we have a molecule, the max number of stereoisomers that we can have is going to be equal to 2 to the n, where n equals the number of RS or EZ stereosides. And then I'm going to remind ourselves of what an enantiomer is, because we're going to find that not everything is an enantiomer, but they can still be stereoisomers. And so an enantiomer, I always use the phrase special pair, and it's because they are a special pair, right there. It's non-superimposable mirror images. They look identical to each other through a mirror, but they are not, in fact, the same thing. And so, for example, let's take a look at a molecule. What we can say is that, let's see, if this molecule right here, let's draw a double bond there. Now let's put a bromine there. Okay, so how many different locations do we have where we can have either RS stereochemistry or EZ stereochemistry? Well, we have a double bond, right? And so if we were going to give a designation to that double bond, we have groups on opposite sides, right? So of course here we've got a hydrogen. Here we've got a hydrogen, and so in terms of priority, we would say that, well, this is higher, and whatever's over here is higher. So if our higher priority groups are on opposite sides, do we give an E or a Z to it? We give it an E designation. Remember, they end up being backwards. All the groups on E are on the same side, so of course that refers to a double bond where they're on the opposite sides, and vice versa with the Z. And then what about this location right here? Do you think this would be a chiral center? Yeah, it would be, because remember, there's also this implied hydrogen here. It's going to be on a wedge. And so we've got a hydrogen there, so let's prioritize. Hydrogen, what is it? 1, 2, 3, 4. It is 4, always. And then we've got a bromine, and so the others are carbons, so what's the bromine? Definitely 1. All right, so then basically we've got a classifier, 2 other groups, and so here we've got a CH3, here we've got a carbon connected to another carbon, and so what's going to be higher in priority? It's going to be the top one, right? Because of that second carbon. So we'd say this is 2, and this is 3. All right, so then we can use the hand rule again, and so our hydrogen's coming towards us, and so if we point our thumb in that direction and then use our fingers to curl, are we able to go 1, 2, 3? Yes. We in fact are, and so that's going to be what letter? R. All right, so we've got an R stereocenter there. Okay, so we can also imagine, and there's a really, really key point to what I'm doing here, so pay attention as closely as possible. Let's take the mirror image, and what would that be? So we'd have something that looks like this. Our bromine is still on a dash. Our hydrogen is still on a wedge, and we still have that chiral center. Now, we've put it through, or we're looking through the mirror at this opposite side, and so if it was R in this image, what is it going to be here? Yeah, it's now become S, and so that is absolutely true. Anytime we've got an R or S label, the enantiomer will have the other label. So what we've got here is an S, but that double bond, is that E or Z? It's still E, right? And so that's a really, really, really key point, is when we talk about enantiomers, the RS label is going to change, but the EZ label is going to stay the exact same. All right, so we've got what we could call RE here, and we've got SE here. And so the relationship between these two things are they are in fact enantiomers. And so a big key point is that we can say enantiomers have the same EZ orientation, but the opposite RS orientation. And so when we look at pairs of molecules and we need to decide are they enantiomers or are they not enantiomers, it can become less important that we actually see the structures themselves. If we know the actual labels already, if I gave those to you, you should know just from looking at the labels whether or not those are enantiomers, right? Because the RS would be swapped and the EZ would be the same. All right, so in this molecule, when we talk about the total number of stereocenters, we say it's 2 to the n, where the n equals the number of RS or EZ. So what is our n in this case? So basically, how many sites are there that we have to give a label to? There's 2, right? And so we'd say our n is 2. So how many possible stereo isomers are there? There's 4, right? So we have 2 squared equals 4 possible stereoisomers. And so we want to consider all of the possibilities. All right, so what we've got is this, which we've called RE. So we'll call that letter A. And then we had its mirror image. And we called that SE. All right, so we're using E twice here, but what have we not used? Yeah, we haven't used Z yet, and so we need to also think about the possibilities where the double bond is actually in a Z configuration. And so when we do, we can draw it out such that it looks like this. Now, we've kept our molecule oriented very similar to this. The only thing that's changed is the double bond. And so if this is an R stereocenter, what is this stereocenter? It should be the same, right? And so it also is R. So we've got R, but then we've got Z for the double bond. And so we could say that this is RZ. And then finally, we need to show the example of SZ. And so we can draw it like this. All right, so our chiral center here looks pretty much identical to the chiral center here, except for this change in the double bond, and so it too is going to be S, but we've changed our double bond to now be Z. All right, SZ. So let's give these things names. Let's call this A, B, C, and D. All right, so now let's talk about the relationships between these two. It's going to be an important skill as we go forward. So what we could have is we have the relationship between A and B. Now, those are mirror images of each other, and so anytime we have a special pair where we have non-imposable mirror images, what do we call that relationship? Those are most certainly enantiomers, right? So I'm going to put an E to designate enantiomers. Likewise, we have C and D. Are those mirror images of each other? They definitely are, and so what we could say is that C and D are also enantiomers. We find that enantiomers always involve pairs. There's always two enantiomers. They come together. Now, A and C, are they stereoisomers of each other? Do they have the same connectivity? They do. Do they have the same spatial orientation? They don't. All right, so they're stereoisomers that aren't enantiomers. What name are we going to give to that, or to A and C to describe their relationship? Starts with a D. All right, let's define it. This is a diastereomer. And this sounds super complicated, but give me 15 seconds to see my definition of a diastereomer. A diastereomer is going to be any stereoisomer that is not an enantiomer. That's it. It sounds really, really complicated, but it's really not. So we've got two possibilities. We've got our huge set of stereoisomers, and then in that set of stereoisomers, we have special pairs, right? Mirror images that aren't superimposable, and we say, all right, those are enantiomers. Those get a special name. Everything else that is not an enantiomer is a diastereomer. That's all it is. And so A and C, they're not mirror images, and so they're diastereomers. B and D, what's that relationship? They're diastereomers. A and D, what's that relationship? They're diastereomers. Basically, everything that is not an enantiomer is a diastereomer. And so what we always want to be able to do is look at two molecules and determine, are they an enantiomer? Well, first off, are they a stereoisomer of each other? And then furthermore, we want to go down a subset and say, well, either they are an enantiomer of each other or they are diastereomers of each other. And so we want to be able to recognize that. All right, let's do another example. So this next example, we'll put a hydroxyl and a methyl up here. Down here, we'll put a bromine, and then a methyl. Okay, so, do we have any chiral centers in this molecule? Yeah, we should have one there and one there, right? So in each case, we have a central carbon that's bonded to 4 different groups. It's on a ring, but obviously, from this chiral center counting left, you have a different molecule as we count right. And so there's certainly 2 different groups. In assigning priorities, we would say that our hydroxyl is first priority. We would say that this carbon is second, third, and fourth. All right, so why is that? So 2 through 4, ultimately, they're all carbons, right? So we want to look for the second point of connection. So here, well, this is just a carbon connected to 3 hydrogens. And so that's certainly going to be less than this carbon attached to a carbon, or this carbon attached to a carbon, right? So we assign this 4, and then it's basically between these 2. And so what we find is that over here we just have a bunch of carbons and hydrogens, but over here we have this bromine attached. And so basically we've swapped out a hydrogen here for a bromine, and so what's heavier? A bromine. And so what we'll roll with is say, well, this weighs 2, and then that weighs 3. And so again, we just want to use our thumbs. So in this case, we've got our group number 4 going back, and so let's see, we can do this. Can I count 1, 2, 3 with my right hand? Yeah, if I tried the other way, I've got my thumb back, I would count 1 to 3, and so that's no good. So it would be R, because we're able to use our right hand. And so for the other chiral center, we want to do the same thing. We need to just reprioritize everything and then determine is it R or S. And so what we'd end up with is bromine will be 1. Again, our methyl will be 4. And then we'd end up with 2 and 3. And so basically the logic is the same. So bromine's the heaviest. It's going to be number 1. This carbon's attached to 3 hydrogens, so it's going to be our lowest priority. And then we see, well, if we go up this way, we hit an oxygen. If we go this way, it's just carbons and hydrogens. And so this way it gets number 2. All right, so same thing. Let's see if we use our left hand. We've got our group number 4 coming towards us. Can we count 1, 2, 3 with our left hands? No, but with our right hand, it's coming towards us, and so we can count 1, 2, 3. And so we see that that stereocenter is also R. All right, so we've got R, R. All right, so there's 2 chiral centers. How many possible stereoisomers are there? There's 4, and so we don't need to draw them out to think about what they are. We can just say, well, we've got RR. What would the enantiomer of RR be? So when it comes to RS designation, do they always swap in enantiomers or do they stay the same? They're the opposite, and so the enantiomer of RR is going to be SS. And so likewise, we could also have different letters, so we could have RS. Now, the relationship between RR and RS, are those mirror images of each other? They're not. So what are they? They're diastereomers. They're not mirror images, they're diastereomers. It's that simple. All right, so then the enantiomer of R and S, what would we call that? SR. The relationship between SS and SR, what is it? They're diastereomers. What's this relationship? Diastereomers. What you're going to find is in molecules where you have different possibilities for stereoisomers, there's typically going to be more things that could be described as diastereomers than things that could be described as enantiomers. Because remember, enantiomers are a special pair. Good question?
How did you count? Did you go over how you counted with your hand the first part?
Yeah, for the first one, it's just, so we've got an oxygen, so that's number 1. Here it's just a CH3, so we've got carbon, carbon, carbon.
Oh, I understand that, but just the motion with your hand.
Yep, and so what it is our group number 4 is going back in the board. So with our left hand, if we count, we see my fingers are at 1 and they're going to curl to 3, right? So that's no good. But with my right hand, my thumb going this way, we start at 1 and then it curls to 2. And so that since it's my right hand, it's going to be the R stereo label. Yeah. Okay, let's see. So, to summarize this little section, which I know in the book, anywhere you read about this, it ends up sounding way more complicated, but it can pretty much be summarized as if all chiral centers are flipped, but this does not include EZ centers for reasons that we've seen above, then we've got enantiomers. And then pretty much, if not, then we have diastereomers. All right, so diastereomers, anything that is not a perfect mirror image of the other stereoisomer in question. Okay, so we've got a few minutes. We'll just go for 2 or 3 and call it a day. So I just want to start the next section. That's going to be section 6. So we've been talking about chiral centers. We've been looking at individual carbons and trying to determine if there's stereochemistry at those carbons. But we're going to take it a little further in the next section. Instead of just talking about particular carbons, we're going to talk about molecules as a whole. Are they chiral or are they achiral? So we'll call this chiral molecules. We'll see how it pertains to symmetry. And so what we can say is that chiral molecules have a non-identical mirror image. So we know this. And really, any object that has a non-identical mirror image is a chiral object. But when we talk about chiral molecules, as in regards to chiral centers, there are specific parts of a molecule that can be chiral. We want to say that chiral molecules always have an enantiomer. And so the only reason I would ever bring a section like this up is, do you think it's always going to be the case that we have a molecule with a chiral center? Are they always going to be chiral molecules? It's not going to be the case. Otherwise, we wouldn't have this section. And so we're going to leave the specifics for Wednesday. But the thing to remember about this section is, if I ever asked you, is a molecule chiral? You just think to yourself, well, does the molecule have an enantiomer? If it does, then yeah, it's chiral. If it doesn't, well, then it's achiral. All right, so we'll ask ourselves the question. It'll basically lead us into Wednesday. We'll say, is a molecule with chiral centers always chiral itself? And our answer to that is, unfortunately, no. All right, so we'll leave that for Wednesday, and yeah, we'll just call it a day.